Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Houston, we have a problem. Today we're going to talk, or continue, I should say, our conversation about energy. So, big topic of what is energy. Energy is a weird concept. What actually is it? And we're going to get there, but we're going to get there kind of a roundabout way. I want to talk about the units of energy. That's kind of weird. The units on energy are a kilogram, meter squared per second squared. What? Yeah, oftentimes we call that, actually we do call it a joule. And a joule is a J. Now you may be familiar with another unit of energy if you are from the United States, and that is called the calorie. So when you buy a candy bar or just any food, you look at the label, it says it's got so many calories of energy in it. But joules, calories, there's 4.18 joules in a calorie, as it turns out. But it's got three dimensions: mass, distance, and time. And so, what is it? Well, again, it's not so easy to explain it until we go a little deeper. So I'm not going to talk about what it is just yet, because it relates to this big concept. And I referred to this in the previous video. And I talked about the conservation of energy. And in the conservation of energy, it says that energy is that energy cannot be created or destroyed. It can only be transformed. Like we said in the previous video, you've got kinetic energy, you've got spring energy, you've got gravitational potential energy, all these different types of energy, and you can convert one type to the next, but the amount of energy, basically like in the universe, is constant. We can only change from one kind to the next. And even as I've got lights right above me, we've got the lights are producing electricity, so electrical energy, is producing light energy, details and all that, and then it's shining on to the screen, on my face, or on the screen, or whatever. And so we are transferring the energy. And actually, if you really go back, where did the energy come from before the lights? They burned some coal or some natural gas at a plant many, many miles away from here, and that energy has been moved to here, to the school, and what I'm making the video. Okay, so that's what we call the conservation energy. It's the law. It's the law of the conservation energy. You can't create or destroy energy. Which leads us to the big concept of work. So to understand work is still energy. It's still going to be measured in joules. And so like our diagram we saw earlier here in the previous video, is that if you have a system and there's some kind of energy transformation, and that energy transformation can either come out as heat or as work. And you can also have something do work to the system. It goes back and forth. And that leads us to an important equation. It's related to the law of conservation of energy, and that you can't create or destroy energy, but if there's a change in the energy, so if you add up all of the kinetic energy and all the thermal energy and all the different kinds of energies that we've talked about, if there's any leftover energy, it's work. Or another way to say that is the change in energy is the work. All right, so let's jot that down. And then it turns out that there is an equation for work. And it's a very simple equation. Work is going to be some force times the distance. So force times distance. So we've measured forces before, newtons in this kind of business. We measure things in newtons. So if you know that if you can take an object and apply a force over a distance, and that's a net force in a distance, then you've done work. So if I push on the board, there's a glass board in front of me, I push on the board doesn't move. But as I move this pin across, I am applying a force, and it's over a distance, so I am doing work on this. So I mean, I could stand and I can hold some heavy weights, and I'm holding. Technically, I'm not doing any work because I'm not moving the weights. Now, you say, wait a second, my muscles will be getting better because I'm working in the weight room. And, I guess at the internal point, there's some contraction of the muscles, so there's work happening, and that's why your muscles will grow as you're exercising. But in a certain sense, since I'm holding two weights right here, and they have the exact, I'm not moving at all, then I'm not doing any work. So what is energy? So we finally get into what energy is. It is the ability. So I can push on this and apply force to the table or whatever it might be, and I have the ability to do work, but it isn't work until you actually do the work, or actually move it. You move it across some distance. So let's now do a couple of work problems. So problem number one, we got a book lying on a table that's 0.76 meters tall. You pick it up and place it on a bookshelf 2.2 meters above the floor. Draw a picture. We've got a table that's 2.2 meters. It's lying on a 0.76 meter high table. So I got a book right here. And I'm going to then put it on a bookshelf again. So I have this 1.6 kilogram book. It's lying on a table, so the table is 0.76 meters from here to here. But I'm going to go take this book, and I'm going to put it way up high here, and it's now 2.2 meters above the floor. How much work have I done? All right. So first of all, let's talk about if work is force times distance. The force on the book is going to be what's holding it to the table is gravity. So force times distance, the force, well, let's do the force. If you recall, F force equals ma, a, and in this case, we're saying mg, and we're on the Earth, so that's 9.8. So the force would be equal to 1.6 times 9.8. I get 15.6 newtons, so this will be 15.6 newtons times the distance. Now, tricky question here is we're raising it from 0.76 to 2.2. So, and this would be, they're both in meters, aren't they? Yeah. So I'm just saying 2.2 minus 0.76, and I get 1.44 meters. So we're going to multiply these two numbers, and I get 22.5. Now this would be in joules. Now let's talk about this because actually during this process, how much work does gravity do to the book? Gravity is always downward, so it will do negative 22.5 joules of work. And during this process, how much work as you take your hand and you lift the book, the opposite will be positive 22.5 joules. So that's how you would answer this question. And now we have another question. We got Hans Full is pulling a rope. Hans Full, that's funny. To drag his backpack to school across the ice, he pulls upwards and rightwards with a force of 22.9 newtons. So he's got his backpack, he's dragging it, all right, but he's pulling it at an angle, isn't he, which is 35 degrees, and he's pulling it with 22.9 newtons, all right, and he's going to pull it 129 meters. So if work is force times distance, he's only doing work in the x direction, not the y. So what I need to do is I need to find the force in the x direction. There's also the force in the y direction, but that's not necessary in this case. In the x direction, I would say 22.9, the force in the x direction, 22.9 times, this is the cosine, right? Cosine 35, which is equal to 18.8 newtons. And then what you'll do is you'll say 18.8 newtons times 129 meters, and I get 2,419 joules. And that's how much energy would be required, how much work would be done on the backpack as he drags it across the ice. Houston, these problems are not terribly difficult, but it is difficult to wrap your mind around the concept of energy and work. But hey, you're awesome. We'll see you in class.